what we say is that when this dissolves, it breaks up into ions. So even though it's not very soluble, what does dissolve is strong electrolyte. So if something's a strong electrolyte, it doesn't necessarily mean that it's soluble. Now, something could be very insoluble, but still be a strong electrolyte because what does dissolve breaks up into ions. Assuming we don't have much, and we're ignoring ion pairing interactions. Ion pairing interactions could, of course, lead to errors. But this is what we're going to call plus S molar, plus S molar. Normally we use X here, but since we're dealing with solubility, it's just more convenient to call it S because S just relates to solubility, and the solubility of AB is going to equal the constant molar concentration of A in this case, and the molar concentration of B, because everything's a 1-to-1 mole ratio. And so however many moles of AB dissolved per liter, we can get it directly from these. And so this gives us F molar and S molar. And so what we get is a simple expression for the KSP. The KSP is the ion product, that is, A plus X times B minus X concentration, which is just equal to S squared. So the solubility for this type of salt is just equal to the square root of the KSP. So an example of that would be, you can figure out the solubility of silver chloride. Let me just get that by knowing the KSP. So if we have a KSP table, just use this one from University of Rhode Island. And we look for silver, something like silver chloride, or any 1-to-1 salt would be the same. We'll just take the square root of that. Since silver chloride, AgCl, it's not on here. Surprise. I'll pull out the one from our book, but take a little bit of time. So here we have the KSP value, so all I have to do is take the square root of that, and I'll have the solubility. In fact, any 1-to-1 salt, AgBr is the same thing, AgI, AgSCN. This is the thiocyanate ion, SCN minus. Barium carbonate is the same. Barium sulfate, calcium carbonate, cadmium sulfide, iron 2 sulfide, magnesium carbonate. All those are just the square root of the KSP, would be the molar solubility. What other types of salts are we going to see? The other types of salts we have are like AB2 solid. If we have AB2 solid, that's going to form A plus X, plus 2B minus Y, whatever the charge is. Your book doesn't set up ice tables for this, usually, but I like to set up ice tables for all the problems. So we start off with 0 molar. And then if we allow this to dissolve, for every 1 mole of AB2 that dissolves, I'm going to get 1 mole of A plus. So that's the solubility. So this can be plus S here. However, I'm going to get twice as much B. And that means if I get twice as much B, then that's double the solubility, or 2x, molar. And so what we end up with is S molar and 2S molar. Now, when we do the KSP expression, the KSP expression is going to be A plus X, B minus Y squared. And so this is going to equal S times 2S quantity squared, which is going to give us 4S cubed. And therefore, the solubility here is going to equal KSP divided by 4. And what we're going to do is we're going to take the cube root of that, or just the 1/3 power. Okay. So, what would be examples of that here? Let's see. here, lead 2 iodate. Lead 2 iodate, if I want the solubility of the lead 2 iodate, look at that over there. Let's take a look at the table here. The solubility of lead 2 iodate is going to be the KSP divided by 4, and then take this cube root, and then we get the molar solubility of that. What other patterns? Lead 2 chloride, lead 2 iodide, same. Copper 2 iodate. Those iodates aren't very soluble. There's from here, and maybe there are others in this, but what other patterns? Well, we have this one, 2 cations and 1 anion. And so what would that be? Well, you know, that's going to be the same actually, overall, but a little bit different. And so that's an A2B salt. And so if we have an A2B salt, and we're looking at, this is going to split up into 2 A's and 1 B. And so initially we assume nothing has happened. And then we allow it to dissolve. And so this is going to be plus 2S. So for every mole of A2B, we get 2 moles of A. That's going to be double the solubility, and this is going to be the solubility. So the solubility is going to be equal to the B concentration. And so at the end of this, we'll have 2S and S. And for the KSP, it's going to be the A squared times B, which is going to give us 2S plus B squared times S, which is going to give us 4S cubed, which means the solubility again is just going to equal KSP divided by 4. And we'll take the cube root. This isn't the only, I mean, these are the common ones. Of course, we could have, you know, salts that are like more complicated, like a 2 to 3 ratio. If it's a 2 to 3 ratio, then, you know, we just sit there and just do the exact same thing as we did here. So that's the solubility in water. The next type of calculation that we look at is precipitation. Tell me when it's good. Erase. This is okay. Yeah. On the S equals on the bottom right. This one? 1/3. Etc. I was going to say etc. I mean, like, that is, we could figure from it what I'm not going to list all of them. All right. So we have this solubility, how much dissolves in water. You know, solubility is going forward, precipitation is going reverse. So let's look at precipitation. And what we have is, we have the criteria for precipitation. The criteria for precipitation is that Q has to be greater than KSP. And this is called, since this is a Q for KSP, we call it QSP. QSP must be greater than KSP. If QSP is equal to KSP, we call that saturated, but it's not going to precipitate. If QSP is less than KSP, then it's called unsaturated. And so a saturated and an unsaturated solution will not precipitate. However, when QSP is greater than KSP, we call that supersaturated. And that is, it has too much product. That too much product means we have to shift this reverse, and therefore we're going to have to precipitate. And so supersaturated means precipitation will occur. So let's do an example calculation of this. Normally what we do is we mix something. So let's say I have a beaker, and this beaker contains 100 milliliters of 0.100 molar silver nitrate. And to this, I'm going to add 1 drop we'll go with 0.100 molar sodium chloride. Well, the question is, will I see it precipitate? And automatically you'd think, yes, you would see it precipitate because silver chloride's insoluble. But it depends on how insoluble it is. Sometimes it's not enough to see it precipitate. In other words, you might not see it precipitate because you have such a small crystal, it's not visible without the aid of a microscope. And so they say in order to see visible precipitate, it has to be on the order of a milligram of precipitate. If you have less than a milligram of precipitate, then it's very difficult to detect. Or maybe even more, like 10 milligrams is like a match head's worth of precipitate. So will we see it precipitate? And the answer is yeah, we should see it precipitate. But it might be so dilute, we might not see it precipitate. In this case, it's probably fine. And so what we'll do is we'll do step I first. When we do step I, the solution dilution. And so we're going to have 100 milliliters, and one drop is 0.05 milliliters, roughly. About 0.05 milliliters. So the total volume is going to be 100.05 milliliters. And then we figure out the new concentration. For sodium chloride, the dilution factor is quite big because we're going from 0.05 to 100.05. And then we're going to times that by 0.100 molar. And so what does that come out to for concentration? So 0.05 divided by 100.05 times 0.1 gives us a concentration of 4.9975 times 10 to the minus 5 molar. Okay, this is going to equal the chloride concentration because sodium chloride is a strong electrolyte. Soluble salts are strong electrolytes. They break up into the ions completely. And it's a 1-to-1 mole ratio. The same thing with silver nitrate. Silver nitrate is a soluble salt. Soluble salts are strong electrolytes. Those will break up. But the dilution is very mild here. It's just 100 to 100.05 dilution of 0.100 molar. And so this was barely diluted. In fact, it's pretty negligible, but we'll calculate it nonetheless, times 0.1. And this comes out to a 0.09995. And this is going to equal the silver ion concentration here. All right. Even though we're thinking in terms of precipitation, we always write the same equation, the dissolution, that is, we're going from the solid to the ion. But now, if we're thinking precipitation, we want to reverse this. Okay. And so we're given the initial. The initial silver ion concentration is going to be 0.09995 molar. And the initial chloride concentration is going to be 4.9975 times so all we're asking ourselves is, which way is this going to shift? Is this going to shift left? If this shifts left, then we get precipitation. If it doesn't shift left, then we get no precipitation. And so how do we know? This is something we normally didn't do very much of when we're dealing with. But the way we're going to do that is we're going to calculate our K value here, but it's not really our K because we don't know if this is equilibrium, so we're going to call it Q. We're going to calculate our Q value here, which is just going to be the silver ion initial times the chloride ion initial. And we're going to see, is it already at equilibrium? It might already be at equilibrium and it's saturated. And so I'll take my silver ion concentration initial, which is 0.099 or whatever it is, 0.09995. I'm getting mixed up with the numbers. 9995, 995 times 4.9975 times 10 to the minus 5. And so my QSP value here comes out to 4.995 times 10 to the minus 6. Okay, now what we need to do is we need to compare that to K and see how it compares to. Okay, K is 1.56 times 10 to the minus 10. And so this is going to be much greater than KSP. KSP is 1.56 times 10 to the minus 10. And so in other words, silver chloride is not very soluble at all. And so it just takes one drop and you'll see precipitate. Certain ones are a heck of a lot more soluble. So for example, if we compare that to lead-2 chloride, lead-2 chloride is 1.62 times 10 to the minus 5. You know, although this splits up differently, you know, then would we see a precipitate occur here? We'll go ahead and try that. So here, this is going to give us precipitation. We'll see cloudy precipitation form. Okay, now I'm going to do this with lead-2 chloride. Let's compare. So this is going to be 0.100 molar PbCl2. If I add, not PbCl2, PbNO3. Nitrate salts are very common because they're soluble in water. So we're going to use that. Will I see a precipitate occur in this? Well, we would think so because lead-2 chloride is insoluble, but it depends on how insoluble it is. Now we're getting into the finer details of this versus before we were just looking at things qualitatively. And so here, it's the same procedure. We'll do the solution dilution, so we're going to end up with 100.05 milliliters. And then the chloride concentration will be the same, which was what was it, 4.99?
9975 times 10.
Thanks. And then the lead concentration here will be, it's a 1-to-1, because for every one of these, we're going to get that. And so the lead concentration is going to be the same. This is going to be 0.09995 molar. Okay, but this splits up differently, and so the KSP expression is different. Because when we look at the KSP equation, PbCl2 solid goes to Pb2 plus 2Cl minus. Okay. And so our initial now is going to be, for the lead, we're going to have 0.09995 molar. For the chlorides, I'm going to have 4.9975 times 10 to the minus 5 more. This is the total chloride present. Out of the total chloride, I need this ratio. For every lead, I need 2 chlorides. Okay, so that's my initial. I'm going to just check the initial to see if it's already at equilibrium or below or above. And so QSP is going to equal the lead concentration times the chloride concentration squared. And so the lead concentration is going to be 0.09995, and the chloride is 4.9975 times 10 to the minus 5 squared. So let's see what that comes out to. 4.9975 times 10 to the minus 5 squared times 0.09995. This gives us 2.4963 times 10 to the minus 10. Is that what you guys get?
Mm-hmm.
All right, so what does this mean here? Well, we compare it to the KSP. KSP value is 1.62 times 10 to the minus 5. KSP is 1.62 times 10 to the minus 5. So which one's bigger, QSP or KSP? The KSP is bigger, which means no precipitate. No precipitate. It's unsaturated. No. You would just have to add more. Yes. Right. If we need to precipitate out lead, we'd have to add a lot more in one drop. You know, the first drop, nothing's going to happen. And so we just keep adding more and more until we see something happen. We always have to be careful in precipitation. Sometimes when you add a lot of precipitating agent, you have the problem of complexes forming. So for example, if you try to precipitate out lead using iodide, you run the risk of adding too much iodide. You run the risk of adding too much iodide because these types of species form PbI3 minus and PbI4, 2 minus. You know, you add too much iodide and these aqueous species start to form, so your precipitate starts to dissolve. For chloride, it's not a big issue. For silver chloride, it's not a big issue. Maybe a little bit of the dichloroargentate 1 will form, but not a huge amount. And so we could add lots of chloride for the silver precipitation. And the same thing with the lead and the chloride. This is not a big issue, but with iodide, it would be a more significant issue. You know, and how do I know? How you know is we have to look these types of things up. We look these types of things up, and what type of table do we look up? We look it up in what we call a KF table. And we're going to talk about KF in this chapter. But we've already looked at KF tables a little bit. Not in the sense that we looked at the numbers. Let's see if this University of Rhode Island one is. So I look at silver. What types of complexes does silver like to form? And do you see a chloro complex here? So silver, cyano, ethylene diamine tetraacetato, ethylene diamine, amine, thiocyanado, thiosulfato. But I don't see any chloro complexes here, so that means I'm probably pretty safe adding just a huge amount of chloride. Because the more chloride you add, the more Le Chatelier's principle will push this to the left, and that means the less lead you'll have in solution. So if I want to try to precipitate out as much lead as possible, then I'm going to try to shift this to the left. Now let's take a look at another calculation. Okay, how about let's flatten. For lead, do you see any chloro? I do. You run the risk. If you add too much chloride trying to get the lead out, you're not going to get it all out. What's going to happen is it's going to form the trichloroplumate 2 ion, And it's going to dissolve because the trichloroplumate 2 has a K value of 24, which is pretty big. A lot of these Ks are big. Look at this mean. I mean, 10 to the 35, it's huge. So we have to be careful, in our precipitations because, yeah, I could try to increase the chloride, and then try to precipitate more and more lead, but then I get these complex formations, and all of a sudden things get more complex. But for silver, it shouldn't be a problem. It shouldn't be a big issue. In fact, what we could do is we could look at the last problem we did. And so this one, we're going to definitely need more chloride. We don't have enough chloride. To get probably a better picture of this particular, precipitation, we probably should do it simultaneous, taking into consideration complex formation. Okay, the next type of calculation we look at is called percent precipitation. Usually, if you have can we get 100% precipitation? Is that theoretically possible? No. And so what do we call complete precipitation? Yeah. And so, complete precipitation is just defined as arbitrary, but complete precipitation is 99.9% precipitation. And so let's take a look at that last problem that we did, which was the silver chloride, and then see how much precipitation we end up with. And so going back from the last section, we had silver chloride, solid, going to Ag plus chloride. And the initial concentrations here with silver was the, what was it, 0.09995? Triple nine. And the chloride was what, 10 to the minus 5? So 4 zeros. And then it was a 49975. And we said that this is going to precipitate. When I add one drop of this, it's going to precipitate. Now, the question is, how much of the silver will have precipitated, with one drop? What percent of the silver will have precipitated? That one drop. Now, when I look at the K, the KSP value is the KSP value for silver chloride. Now, it depends on what table you get the KSP value from. Our book only has KSP values to 2 sig figs. This table A10 here has it to 3 sig figs, so we'll just go ahead and use this one to 3 sig figs. The KSP value is 1.56 times 10 minus 10. Our book is different. Our book is 1.7. So we're going to see some variation in this, and so it's nice to know what the source is. I think our book's source is, at least I would hope that it's pretty up to date. But let me just take a quick look over here. This looks like our book, doesn't it? Looks like our book. This one says 1.8 times 10 to the minus 10. And so why is there so much variation? That's something we have to be careful of, and be aware of. And so it's important to know the source of it. What does this one say? This one says 1.7 times 10 to the minus 10. So I think this is the same as our book here. Or maybe I'm wrong from my memory. I can't remember. 1.8 times 10 to the minus 10. And that's so required there. Well, there is 1.8 times 10 minus 10.
So out of those 4 or 5 tables we looked at, 1.8 times 10 to the minus 10 seems to be more common. So what I'm going to do is I'm just going to use 1.8 times 10 minus 10. If I don't know which one is the most accurate, I'll just use the more common one. But these are things you note in discussion sections of papers, since there are discrepancies there.
Do they have somewhere where like they keep updated the like more
Yeah.
official ones?
They do.
Okay.
They have it. It's called they update it every year.
Why does it keep changing?
It keeps changing because more and more people do it, and then these are composite averages things, and so it depends on what, because it's history. It depends on how old it is, but it's continually updated. And then sometimes there's no updates of it. So this book here, CRC Handbook of Chemistry and Physics, is updated annually, and so it's their job. And it's expensive. I guess it's not really expensive because it's a lot of work to update everything every year, and then get the most current references of this. And so the 100th edition of this, $250, but you can buy older editions pretty cheap. I mean, the 88th edition. Well, this is the 102nd. This is the anniversary of this thing or whatever.
So this isn't like common, just they're not sharing this with everyone.
No, you have to pay for it. You have to pay for it because it's a lot of work to make sure you have the latest numbers. I have this book myself. The 56th edition. This one. I think this is super old, but this is only $23. And a lot of the data hasn't changed really that much, And this is really handy to have because it's a handbook of chemistry and physics, so it has a bunch of other stuff in there. And so it's worth buying. I mean, even an old edition, it's pretty useful. Because the 102nd edition is $308 on eBay. Well, anyway, they also have this on online as well. You pay for it.
They have a Kindle edition that's cheaper.
Oh, really?
Oh, I'm asking. I'm kidding.
Okay.
I understand why they wouldn't just make it like a subscription platform thing. Because if they're updating it every year, then it's like buying a hard copy of it. It feels useless.
Yeah. Yeah. You're right. Free.
Don't trust it.
Yeah. All right. So we could look up, and this is pretty reliable. If we have the latest edition, it's good. And if you work at let's say if you're at the university, of course they're going to have the latest edition. You can get that, in the lab. So it looks like 1.8. We'll just go with 1.8 times 10 minus 10. That's going to change this a little bit. 1.8 times 10 minus 10, KSP is a little bit bigger, so it makes it a little bit more soluble, but it's still going to precipitate out. There's the orders of magnitude difference between QSP and KSP. But if we have a KSP of 1.8 times 10 minus 10, then which side is favored? The reactant side or the product side? Yeah, it's a very tiny number, so yeah, actually the reactant side is going to be favored. And do you remember when we have it heavily lopsided, we want the change to be small, because if the change is small, we can always use the simplifying assumption. If we leave it as is, the change is going to be big. Why is the change going to be big? Because the reactants are heavily favored. We're going to get lots of precipitation. And if the change is big, then we can't use the simplifying assumption because the percent change is going to be too big, more than 5%. And so normally when we have something like this, what's the first thing we do before we even reset it. And so, in this case, we want to reset it. We're going to reset it to the left. And so what we have to do is we have to look at what is the limiting gradient going backwards. Which one will we lose? All of them. Yeah, the chloride. So what we're going to do is we're going to lose all the chloride. And that means we're going to lose the same, it's a 1-to-1 mole ratio here. So we're going to lose the same amount of silver. We have excess silver, so we can't lose all of it. And then we're going to get plus. Yes, we're going to get plus over here, but we're not going to write it because it's just going to be plus extra pure solid, and that's not going to change its concentration or its activity. And so we kind of ignore it. Yes, we're going to get more solid, but we're going to ignore it because we usually ignore solids and liquids. And so we're going to have our new initial conditions. Our new initial conditions will have chloride at 0 molar. And then the silver ion, we're going to have to calculate that. And it's going to be 0.0995. Minus 0.00499975. And that's going to give me a new initial concentration. So I had this much excess silver, 0.0999 mole excess silver. All right, now, so basically what I did was I precipitated all of it in this step, as much as I could. I precipitated out as much as I could. And now, a tiny bit will dissolve back because, in this case, what is Q? If I calculate Q, Q is going to be 0.0999 times 0, which is 0. Q of 0 is less than KSP, so it's got to shift to the right. It's unsaturated. So what I'm going to do is I precipitate out all of it, and I'm going to let it resaturate. In other words, some of it will dissolve. I can't have 100%. And so this is going to be the minus. Now, no one can call this minus. I mean, minus. This will be plus S, right? Plus S. So the solubility is going to be lower because of the common ion here. This is like a common ion. If this were 0, 0 solubility would be higher, but since we have some initial 0, solubility is going to be lower. So this S is not the solubility in pure water. This S is the solubility when I have some silver ion present. Does that make sense? And the more silver ion or the more chloride ion I have present, the less soluble it's going to become. And so, again, this solubility is not the solubility in pure water that we calculated, that we would have calculated. I don't think we would have calculated, which is just the square root of 1.8. And so equilibrium, we have 0.0999 plus S, and we have small. Okay. And so what this is going to do is we're going to have this as the silver ion concentration, 0.0999 plus S times S. Although the math is not difficult here, I don't want to solve a quadratic if I don't have to. And I'm just going to call this 0.0999 using the simplifying assumption times S. And then we'll just calculate S. So S is going to just be 1.8 times 10 minus 10 divided by this. So I have this sort of my calculator times 1.8 times 10. So I get S is 1.8018 times 10 to the minus 9. This is molar. So the chloride concentration is, okay, so what happens is a little bit redissolves, and that little bit is 1.8018 times 10 to the minus 9 molar. That would be the solubility of silver chloride in the presence of this silver. And then I'm going to add that to 0.0999. And this is going to just be about 0.0999. Anyway, the percent change here, I didn't calculate it, but the percent change is minuscule. The percent change is equal to S over 0.0999. So this is 10 to the minus 9. And this is like 10 to the minus 1, 10 to the minus 2. You know, about 10 to the minus 1 times 10 squared. 10, this is like a 10 to the minus 6% change. So even if I did the quadratic, it wouldn't have made any difference in this particular case. And so this is, resetting is common in this chapter because otherwise the math gets quite difficult. Okay, but I haven't answered. So I know what the solubility is in the presence of this silver, but I want to know what the percent precipitation is. And so how can I figure out what the percent precipitation is? How much of the original silver ion did I precipitate by adding the sodium chloride? Well,
How much of the silver ion?
yeah. Okay, so what I have to do is, this is a little bit tricky. What I have to do is I have to go back to the original silver, not the original silver after solution dilution. So this is my initial. And then I look at how much I have at the end. Not very much precipitated. Can you see that? And so what we're going to do is we're just going to calculate the percent. In order to do this calculation, first, if I want the percent precipitation, the way I have it set up, this is the typical way we have it set up. First, calculate the percent remaining. Percent silver ion remaining. The percent silver ion that remains is this, the silver ion concentration in equilibrium over the silver ion concentration initial. This is not the reset initial, this is the initial after solution dilution. Initial after solution dilution, but before reset. And we'll just multiply by 100%. So the silver ion concentrated equilibrium is 0.0999. The silver ion of equilibrium, the silver concentration at initial would be 0.09995 times 100%. Most of it remains. One drop is not enough to precipitate very much of it, it looks like. So 0.0999 divided by 0.09995 times 100. 99.95%. 99.95% remains in solution, unprecipitated. Okay, next we're going to calculate the percent precipitation. Calculate percent precipitation. Percent precipitation is just equal to 100% minus the percent remaining. And that's going to give us 0.050025% precipitation. We only precipitate out 0.05%. So one drop, we need a lot more than one drop to precipitate out. So a challenge question might be like this, you know, how many drops are required to precipitate out 99.9% of the silver there? I should have raised that. I need this concentration. How many drops are required to precipitate 99.9% of the silver? This wouldn't be a very easy problem here, you know, because we're starting off with 100 milliliters of 0.100 molar silver nitrate. And then to this, we're adding drop by drop, 0.100 molar sodium chloride. The problem with this is solution dilution. You see, because with each drop, I'm diluting it. And so that's, whereas in that last problem, it was kind of static, because after solution dilution, I'm not adding more liquids. And so the concentrations are changing. And so it's not a simple matter as this. For example, if I wanted to precipitate out 99, this is 100%, let's say, 1.100. It's not a simple matter of just going to, 0.0001 molar remaining. If I have 0.0001 molar remaining, but the volume changed tremendously from this. Remember, this is the concentration before solution dilution. The concentration after solution dilution is different. And the concentration after solution dilution is the one we set as our initial in figuring out the percentage. And we don't know that because we don't know how much we're adding. And so it makes it a bit more difficult to do this. But not impossible, because the way we do it is we do all these problems the same way. You know, we start off with solution dilution. We call it X drops. You know, X drops. X drops is would be X, in terms of milliliters, would be X times 0.05 milliliters. And so what we do is we kind of set up the same type of solution dilution type deal. In this particular problem, it might be easier to use millimoles. You know, there are advantages to doing millimoles. And so the final volume will be 100 plus X times 0.05 milliliters. And then what we'll do is we'll figure out the concentrations. The concentration for chloride is just going to be X times 0.05 keep it simple, divided by 100 plus 0.05x times 0.100. This is going to be what we call chloride initial. The silver ion initial will equal 100 divided by 100 plus 0.05x times 0.100 molar. That's our initial. What should be our equilibrium silver concentration? Our equilibrium silver, well, we can set up the ice table here. And so the next step would be to set up the ice table, which is going to be silver chloride solid. Goes to silver ion plus chloride ion here. And the initial silver ion is just 100 over 100 plus, actually 100 times 0.1 is what? Let me just do that so I don't have to worry too much. It is just 100 times 0.1 is just 10, right? And so it'd be 10 divided by 100 plus 0.05. And the chloride, what's 0.05 times 0.1? 0.005. Right? And so this would be 0.005x over 100 plus 0.05x. Okay, we've seen this type of problem before if you've been following the homework, although I haven't been posting it as quickly as we should. But we need to know what the final concentration should be. Now once we've done this, once we've added this, we don't have to worry about solution dilution anymore because this is it, right? And so what we have, this is 100% of the silver that we started off with. That's the 100%. And so how much do we have to have remaining at the end? Well, we have to lose. So this is the 100%. And then we're going to lose how much? 99.9% of this. 99.9% would be 99.9 parts out of 100. We're going to lose. So that's 99.9 out of 100 parts of this we're going to lose. That's minus in precipitating out backwards, right? And that means how much are we going to be left with? We're going to be left with at equilibrium 0.1 parts out of 100. So we're going to get 0.1 parts out of 100 remaining because 99.9 parts out of 100 precipitated. And that would be out of the initial concentration, which would be 100 plus 0.05. Okay, we have to do the same thing over here. This is going to be minus 99.9 over 100 times 10 over 100 plus 0.05x. And therefore, the chloride concentration is going to be 0.005x over 100 plus 0.05x. I'll just put parentheses around the whole thing here. Minus 99.9 out of 100 times 10 over 100 plus 0.05x. Okay, then what do? We gotta solve for x. So we need an equation where we can solve for x. So what would that equation be? And that equation is going to have to be the KSP equation. Let's see. So we're going to get the KSP is equal to 1.8 times 10 to the minus 10, which is equal to the silver ion concentration, which is that. Let's do this. 0.1 times 10 is 1, correct? And that would be 1 over 100. 100 times 100, it'd be 10 to the 4th. And then 100 times 0.05 would be 5. So this is going to be, actually maybe we'll just leave it this because then we can factor it out. And so I'll just do 10 divided by 100 is what, 0.1? Yeah. Times 0.1 would be 10 to the minus 2, so 0.01 over 100 plus 0.05x times, let's see what we can do with this one here. So 10 times that would be 999 over 100. Move the decimal 2 over, would be 9.99. So this would be 0.005x over, I'll just put everything over the same thing, minus 9.99 over 100 plus 0.05x. Got it? All right. I'll probably factor this out here, or multiply both sides by this. Multiply both sides by 100 plus 0.05 x squared. So we'll just say etc. Here, I don't want to spend any time doing lots of algebra. Okay, do you see the setup though? The x is going to be the number of times.
Would you ask us a question like this?
I have to ask questions like this, like how many drops or how many milliliters, to do certain things. Not just this, but I've asked questions like how many milliliters would it take to precipitate, or how many milliliters would it take to dissolve? The setups are all the same. It's the same kind of setup. You do the solution dilution, and then you do the ice table, and then you solve for a variable. And so it's not comparable. I'll set it up for the other one. This one I haven't asked. Really. Maybe this math is going to be a headache. So, you want to solve it? Well, you want to solve it for.
I mean, if you're going to give us ones that are going to be easier numbers, let's do one of the easier numbers. But if you're going to ask us something exactly like this, I would like to solve it out.
Any minutes? Okay, should we solve this then? Try to? So, what should we do next? Well, I guess we could multiply this out. Maybe that would be okay. And so this would be 0.01 times this, which would be 0.0005 x minus 0.01 10 to the minus 2. We'll move it 0.0999. Okay, and then just these two, which are the same, 100 plus 0.05x quantity squared. we'll get 1.8 times 10 to the minus 10 times 100 plus 0.05x squared is equal to 0.0005x minus 0.0999. All right, so what should we do next here? Probably get it into quadratic form, just multiply out this binomial. Okay, 1.8 times 10 to the minus 10. So this is going to be 0.05 squared. So 5 times, this would be 25 times 10 to the minus 2. So that would be 10 to the minus 4x. And then 0.05x times 100 would be 5. So that would be 5x plus 5x would be 10x. Plus 100 times 100 would be 10,000. So then I'm going to multiply this throughout here. So 1.8 times 10 to the minus 10.
Which one is x squared?
This one, first term. Yeah, square that. 1.8 times 10 to the minus 10 times 25 times 10 to the minus 4. This is 4.5 times 10 to the minus 13 x squared. Plus, this is times 10, so that would be 1.8 times 10 to the minus 9 x. Then this is 10 to the 4th. So 10 to the 4th would be 10 to the minus 6. So this would be 1.8 times 10 to the minus 6. Equal to point. So we're going to add 5 times 10 to the minus 4, both sides here, x. And so we have 4.5 times 10 to the minus 13 x squared plus 0.005 times 1.8 times 10 to the minus 9 is 9 times 10 to the minus 13 x plus, add this to both sides, and so this is going to be 0.099. So 1.8 times 10 to the minus 6, so 0.18 equal to 0. Let's see if it worked.
What happened here? Just x value. It should just be 0.005.
Oh, yeah.
Minus 0.005.
Yeah, I forgot to subtract. I need to subtract it. So it's going to be 1.8 times 10 to the minus 9 minus 0.0005. This is actually it's going to come out to 0.0005. So minus 0.005. And then there's too many decimal places there that we can put anywhere. Okay, does that look right? Okay, let's try this now. Hopefully it works. So A is 4.5 times 10 to the negative 13. B would be negative 0.0005. C would be 0.0999018. If I did the calculation correctly, it'll just take 1.1 billion drops.
Cool. That won't be hard to count.
1.1 billion drops. Is there a way to check our answer? Yes, there is a way to check the answer. The way we check our answer is, do you know how? Yeah, we just plug it in and then see if it works. So what we're going to do is we're just going to plug in X here and then see if this works as far as ice table goes. So let's try that. Maybe do you think we should give up on precipitating out 99.9%? Yeah, if this is accurate, yeah. So we'll get it, but maybe so silver chloride, silver chloride. So we'll put in this value here. So I'm going to just do this in the denominator first. So 0.05. Let's go back to computational load. 0.05 times, I'm going to go 1.1111 times 10 to the 9. Okay, plus 100, because 100 is not going to make any difference to that. And then I'm going to invert that. Times 10 divided by 100 times 99.9. So I get 1.7982 times 10 to the minus 7 molar. That's after a huge amount of solution dilution here that we're going to get. Okay, for the chloride, 0.05 times 1. We'll just do a short quadruple 1 times 10 to the 9th. Plus 100, which is not going to make any difference. Convert that times 10 divided by 100 times 99. Oops, shoot, this wrong one. This one. Can we do that? Okay, the chloride I get as, what did you get? One molar. Is that what you got?
No, but I think I did it.
No, I did it wrong. I had to have done it wrong because we're adding 0.1 molar. If we're adding 0.1 molar and we're doing solution dilution, it cannot get more concentrated. You got 0.1? 0.1 is okay.
9.
Okay, 0.09? Yeah, 0.09. 0.09 something?
0.008.
All right. 0.09008. That's almost at infinite, you know, what we call infinite dilution. Infinite dilution would be you add so much 0.1 molar sodium chloride that the solution becomes 0.1 molar, you know, at infinite dilution. And so if I hit 1 molar, it's impossible because if it were pure sodium chloride solution, the max it could get was 0.1, and that would be at infinite, so that there's barely any negligible here. So I don't know. That makes sense. So what we're going to do here is, what do we do? Typically, we will.
Plug it into KSP.
We could plug it into KSP. There are two things we could do here. We could just do it as is. It's got a shift left, or we reset it. Well, we'll just reset it. So this is going to go to 0. And then what's this one gonna go to? So that would be 0.09008 minus 1.7982 times 10 to the minus 7. Which is going to give us the same 0.09008. I wanted to do the other digits, but my calculator doesn't carry it. That's all right. So this is my reset initial. Then the change is going to be plus S. And so at equilibrium, I'm going to have S and then 0.09008 plus S. And let's plug it into K and solve for S. So we plug it into K, the S, and I think the simplifying assumption should work here. And so this just comes out to S times 0.09008. S is equal to, KSP was 1.8 times 10 to the minus 10, so this times 1.8 times 10 to the minus 10 gives us 1.6214 times 10 to the negative 11. And so we end up with 1.6214 times 10 to the negative 11. Okay, then what we're going to do is we're going to look at the percent remaining. The percent remaining will be the equilibrium amount that remains divided by the initial after solution dilution. And so this is the initial after solution dilution. This is the initial after reset. And so divided by 1.7982 times 10 to the negative 7 times 100. And so we have percent remaining. I'm just going to show this off. Is equal to 0.009%, etc. And the percent precipitation would be 100 would be 99.99%. We wanted 99.9% precipitation, right? So, but rounding errors are probably account for it. Okay. But you're going to have to add a billion drops, which is impossible, of course. I'll stop here.